sliding, please.
Okay, good evening. It's nice to be here back in Chennai again, and thank you so much for the opportunity to present some of our work today in front of you. My name, as I was just introduced, is Kaushik Vishwanathan. I'm a faculty in the Mechanical Engineering Department at IISc in Bangalore. And our group is technically called a manufacturing group, but we do a lot of mechanics, mostly continuum scale mechanics, fracture, failure, things like that. So hopefully there will be a different perspective to some of the talks that we had earlier today. Okay, the basic context for the talk is sliding friction, and we all know sliding friction very well. This is an image of the Himalayan fault that runs across, at the foothills of the Himalayas, and you can have slip events, and these emit seismic waves, and you feel them as earthquakes and so on. And right from this scale, which is very large, all the way to something very small and relatable, I suppose, the mechanics of what happens when these bodies slide turns out to be remarkably similar. So if you ask the question how a body actually slides, right? I mean, the textbook answer that I suppose all of us are familiar with was given by Coulomb, Amontons and Coulomb. And of course, this says that if you increase the load, let's say you're trying to slide this body and this guy is kept stationary. If you increase the load being applied to the left from 0 onward in the positive direction towards the right, then the body remains stationary until the load reaches the static friction threshold, at which point it starts moving, right? This is the classical Coulomb friction model, and it's characterized by the sudden onset of slip at this particular value. This F is given by the friction coefficient times the normal load. Now this is not, this is obviously not the entire picture, and we know, for example, from the vast earthquake literature that there are a whole range of these slip events that happen, and they're not all happening continuously, because if it was happening continuously, we'll all be moving around. And so there is a power law distribution, the Gutenberg-Richter law, from which the Richter scale is derived, as some of you are probably aware. And so that tells you that there is some inhomogeneity associated with this process, right, inherently. What people commonly do, at least in the engineering literature to a large degree, and also in some of the physics literature, the geophysics literature, is you start with these two bodies as being completely rigid, and you postulate that the friction law at the interface is not this Coulomb friction, but it's some velocity dependent rate and state type of law, right? So you postulate the existence of an internal variable, usually called an aging parameter, and you either have velocity strengthening or velocity weakening depending on the physical system. Again, all this is done at the continuum scale, and this is used, for example, to explain things like stick slip, frictional slip instabilities, and so on. Now the situation, there is a different dimension to the situation, and that came about in the year 1971, and there was a paper by a gentleman called Adolf Schalamak, and this was perhaps for the first time that the compliance of the system or compliance of the elastic body became important, right? People knew that elastic systems have compliance, and so when you slide, some degree of that elasticity is going to be, going to show up in the actual sliding process. But the demonstration was done very dramatically by Schalamak. What he did was very simple. He had a hemispherical lens. He had a rubber, piece of rubber, and he'd slit the lens on the rubber. And the lens being transparent could be imaged from the top. And if you looked at the interface, the contact interface, you will see that there are lots of slip precursors that propagate past the interface, and this is what causes slip. The common analogy for this is if you take a carpet on the floor and you want to move the carpet by some amount, you can either slide the entire carpet along, or you can create a loop in the carpet and kick it all the way to the front, right? And these waves of detachment, he called these waves of detachment, they've been called Schalamak waves ever since this paper came out. And they've been observed in a lot of these soft materials, soft systems, and so on. So that really begs the question, when does this elasticity become important, right? I mean, on the one hand, you can make the friction law more complex and have rigid bodies. On the other hand, you can make the friction law simple and make the elasticity more accurate. So when does this type of distinction, when is it important? Now it's critical to realize that there are two time scales in this problem. So let's say you're pushing with some velocity V0 and the length of the interface is L. There is something called a slip time, which is the length of the interface divided by some typical elastic wave speed. So this could be the Rayleigh wave speed or the shear wave speed in the material. They're all of the same order of magnitude. So we'll assume one of them. When you divide this, you get a velocity scale. And in most common situations, the time scale for this slip is much lesser than the experimental time scale, the time scale for observations. So what you see as being instantaneous is in reality not, but appears instantaneous because the time scale for that is very small. Now there are obviously two ways to increase this time scale Ts. You can either make the length of the contact very long, or you can make the elastic wave speed very small. In earthquakes, the first thing happens, the length is very long. And in very compliant materials and soft materials, the elastic wave speed goes down because the modulus is lower, right? When that happens, the Ts goes up, and at some point when it becomes comparable to the experimental time scale, the interface dynamics becomes important. So it's no longer just a rigid block with some friction law, but it's an elastic block potentially with a complicated friction law that you have to work out. And people have found, I'm not citing some of the literature here, but there is at least a couple of decades of experimental observations where people have reported rupture fronts at the interface causing nucleation to slip. Okay, so the static body starts sliding, some rupture happens, and then when the rupture propagates to varying degrees under various conditions, the body starts sliding. That's the common picture that people have. So the work I'm going to describe will be in two parts. The first part is going to ask the question, what types of fronts can occur at the interface? This is work that's already been published, so I'll go over it a little bit quickly. I'll give you a reference to some of the details. The reason I've included it is because the second part depends on this, so in the interest of continuity, I have to give some of these details. And when discussing what types of fronts can occur, I'll talk about some in situ imaging experiments on a typical, prototypical soft contact. And we'll discuss what sets the velocity scale. It turns out that that's a non-trivial question. And we'll discuss some properties of these rupture fronts or waves. And I'll very quickly sketch out a theory for the propagation of these waves. Okay, this theory is, again, like I said, this stuff is published. The theory is, severely limited. We'll see the limitations. And that leads to the second part, which asks the question why they occur, right? And for this, I'll describe a lattice model. This work is not yet published. There is a preprint to which I'll put a reference out. And the idea of using a lattice model is to look at finite dimensions and the role of boundary conditions and use that to determine how these waves nucleate. That's a very difficult problem. Even if you go back to fracture, Griffith theory tells you that a crack will propagate at a certain stress. You have various variations of that. But what forms the crack is a question that's very hard to answer, right? The nucleation problem is very difficult to address. The propagation problem is much easier because you can throw electrodynamics at the problem. And we'll see that as we go along this path, when we do this some of these lattice dynamics calculations, what appears to be a friction problem starts transitioning into an explicit fracture problem, and then that starts branching out into other domains. I'll give some details of this at the end. There are lots of very interesting analogies. We have not probed all of them yet. Hopefully there will be some point of discussion based on some of these ideas. Okay, so the first part is to talk about what fronts we see, and the emphasis is on the word see. Hopefully why this emphasis is on the word see will be clear a little later on. And this is the reference for this work. So here is a basic experimental setup. So we want to slide two bodies, and we want to look at the interface and basically observe the dynamics, right? How it starts sliding, what the rate of sliding is, and so on. So here is what we do. There is a rigid body here, a optically transparent body, and then there's an optically transparent polymer, and it's backlit, and you take a high-speed camera and look at the interface. When you bring these two into contact, there is a slight curvature on the front face, and so there is a line contact initially, and this light gray patch is where if you put a normal load, there will be a patch of contact. So this is like a contact channel, right? So if you look at the camera image, it looks something like this, and you pull or you push with a velocity V naught far away from the interface on the left side. Okay, and that is what you will see. So this region is the contact region, and the dark region is out of contact, right? Again, some of you have probably seen these results before. Please bear with me because I'll sort of use this to set the stage for what comes next. Okay, so here I have two different conditions. I have a large contact, a large normal load, small normal load. The exact conditions don't matter for now, as it will turn out in the second part of the talk. But the configuration is otherwise identical. The velocity on the left pulling remote velocity is slightly larger than the right, maybe 2.5 times on the right. The contact size is larger, the normal load is larger, so the contact patch size is bigger. And it's being pulled at a constant speed. So far away from the interface, the material is moving at a constant speed. So if you observe what happens, and again this size, there's a scale bar there, tells you the size is about a millimeter, just over a millimeter, the contact width. Okay, sliding is from left to right. So this is what you see, right? If this is just one slip event, there are a few features. I just run this movie a couple of times so that some of those can be appreciated. If you look outside of the contact zone, yes, this is just in contact. So some part of it is in contact. There is an air gap where there is no contact. There is an air gap. So the indenting system is actually like this with a very large radius of curvature. So you put it in contact. So that's what you need that to get the image. Otherwise you'll get a patchy image. If you look at points that are outside the contact, they move at uniform speed. But then, for example, if you look at this point within the contact, it remains stationary until this detachment zone goes past it, right? And now it jumps by a certain amount. So it's here, the wave comes, it jumps to here, right? Oh, here, huh? Okay, yeah. So you can see that the interface remains stationary until the wave comes, and then once the wave comes, it jumps. All right, now you change the normal load, change the velocities. Again, details of how much it's reduced and so on are second order information right now. But if you change that and do the same experiment, you will see something very different. Again, you slide in the same direction, but now you see a wave go in the opposite direction, right? And just keep your maybe eyes peeled out on this point, which is initially here, now it moves here. So the point is moving in the direction you're moving the body in, but the wave is going the other way. Okay? And there are two distinct types of waves, right? The features are different, their wave speeds are a little different, and so on. Now the key sort of message that I'd like to sort of get across here is that the two waves, you can construct what are called space-time diagrams for these waves. You take one location on the interface and stack up images of the same location as a function of time. In this case, it's stacked vertically. And you can measure the slope, it will give you the velocity. The key feature is that both of them travel much smaller than the Rayleigh wave speed. Right? Now you would expect if there is a slip event and elasticity is the one that's dominating these slip events, you would expect some correlation with the elastic wave speed. In this case, the generalized Rayleigh wave speed or CR. But it's not true. Okay, both waves go much slower than the Rayleigh wave speed. The other feature that I also want to perhaps highlight is that both waves show distinct force signatures. So if you just take the overall force, remember this is a velocity controlled experiment, the total force is an integral of the shear stress on the interface, and it oscillates like this for the, I'm calling the plus wave the one that goes in the same direction as motion, and the minus wave is the one that goes opposite, right? And the force traces are very distinct. In the second case, you see it starts falling off. Eventually, the contact patch starts narrowing, even though the normal load is kept the same. Now, the question that comes up naturally is how do you explain these types of waves? If you assume, let's say something like this, your body is assumed rigid, the indenter or the rigid cylindrical piece that is kept in contact is kept assumed rigid. The elastic medium, is let's say going from z equal to 0 downward, and it's being pulled. Like I said, the same boundary conditions. We're drawing a 2D cross section of it. Usually, when you talk about wave motion, you have a wave equation, which is a hyperbolic PDE. So in 1D, you have something that looks like this, right? And phi could be sound, pressure. If you have a longitudinal sound wave, it could be E bar, B bar, and so on. But there's a wave equation, there's a wave speed. Now in elasticity, there are two wave speeds, as most of you I'm sure are aware. There is a shear wave and the longitudinal wave, or the tangential wave and the shear wave, CT and CL, and they're both for this material of the order of 1000 meters per second, right? But our waves go at about 100 millimeters per second, so it's several orders of magnitude slower. This is a rubber, yes. There is also a viscoelastic time scale effect. They are lower, yes. So this one is hardened, so the cross-linking density is higher. So it's about 800-ish meters per second. So it's order of magnitude, right? But typically, if you have a very flexible rubber, you're looking at a couple of 100 meters per second. Right? Now, the problem with trying to recover these types of waves from elastodynamics is twofold. Firstly, of course, the wave speed is very low, so there's really not much you can do because any wave that you try to describe with this elastodynamic framework will depend on those two wave speeds. The propagation speed will depend on those two wave speeds. And the second problem is we don't know how they nucleate, right? This is really the key that we're trying to address in the second part of the talk. So the initial conditions for how these waves form, we don't have much of an idea based on these experiments. We've gone to the side edge of the contact and see how they form and so on. So we have some idea, but then to really get a full picture, you need to look at the cross section. So you need to look at this plane. We're looking at it from above, right, in the experiments. And this plane is very hard to access because the indenter has a curvature, right? So it's difficult to get the initial conditions for this wave problem. I'll describe what we did, and then I'll sketch out, some loosely sketch out the basic procedure. It's not that the derivation is not interesting. It's just I think if we go over the details, we'll probably spend 80% of the time on 20% of the talk. So I try to avoid that to do this. If you take, if you look for elastic solutions that are decaying from the z equal to 0 plane from here, again we assume this is two-dimensional plane strain, so that's an inherent assumption in this entire thing. And you separate out the nucleation, which means you're looking at a steady state propagating wave. So you move to a co-moving frame with the wave speed c. Again, there is no a priori reason for the wave speed to be small or large, but nonetheless just assume there is some wave speed. And the wave speed is a signed quantity, so x plus ct will be in the negative direction, x minus ct is in the positive direction. And we separate the problem out into two parts. We have a region where there is separation. So now the interface is from, let's say, this is in some angular coordinates, but let's say from minus a to plus a you have a detachment in the middle, and then to the left and to the right it remains, the interface remains stuck, right? That's what the experiments tell us. And so we try to put that in to the actual equations and try to model it explicitly, right? So in the separation region, which is in the middle, you have detachment. That's the dark band that propagates. And in the detachment region, you don't have stresses. So it's a stress-free boundary condition. You can change the sigma zz and put an adhesive stress. It doesn't change too many things at the end. But nonetheless, if you assume that it is stress-free here, and it is stuck outside of the contact. So everywhere outside the little separation zone, you have zero velocity, right? Not zero displacement, zero velocity. That's important. And the hat denotes that these variables are at z equal to 0, the plane z equal to 0. The basic idea, the only sort of perhaps non-trivial idea is that we use this c by ct and c by cl as a perturbation parameter, small parameter because it's very less compared to 1, and we do an expansion. This is a singular expansion problem, so you can't set c equal to 0 because that will mean no wave and the whole thing will break down. Nonetheless, you can still do small c by cl perturbation with the understanding that you never reach the c equal to 0 limit. Okay, so that's something that you have to keep in mind. And if you do that, you can reduce this to something called a singular integral equation. You can define the velocity field in the region that is separating. Now remember, the separating region is moving, the stuck region is stuck. So the velocity there is 0, but because the separating region is moving, there is some local interface velocity and the stress is 0, right? And you can replace the interface velocity in terms of two unknown functions, phi and omega, and you can write down dual series equation, and then you can do a transform and bring it down to this form. If you've done fractal mechanics, you've seen this type of procedure before using complex functions. And these two are called integral equations. They're not just integral equations because of course phi appears in the phi and omega are unknown. You're trying to find the interface velocities. So they appear inside the integral and outside, and these two are coupled. So you have to solve them simultaneously to get phi and omega. They're not just any ordinary integral equations, but they're singular integral equations because the integral contains a singularity in this term. So when xi appears, when eta comes close to xi or xi comes close to eta, xi is the variable being integrated. this term will blow up, right? And likewise, this term will also blow up. So there is a special class of these integral equations that you can solve using complex functions. If you make the approximation that the solid is incompressible, which is you send the longitudinal wave speed to infinity, the perturbation series in C can be terminated at the leading order in C by Ct. C by Cl terms go to 0, but C by Ct doesn't, right? And that's the distinction you have to make. If you put C by Ct also equal to 0, the whole thing will blow up because it's a singular problem. If you do that, then you can decouple these equations. So when the material is incompressible, you can decouple the two equations and you can get the phi equation separately, omega equation separately. You have auxiliary conditions. These come from some, this comes from the total load and this comes from some compatibility with the remote velocity. These equations you can invert in closed form with the cotangent kernel. It's a well-known singular integral equation that can be inverted in closed form. And it gives us some solutions, right? I won't write down the solution, but I'll tell you what the solutions tell us. Okay, there are three parameters. There is the dimensionless wave speed, which is C by V naught. V naught is the speed at which you are pushing, right? And there is a wave number, which is V naught by C delta x. Delta x is the amount of slip that a single wave causes. And there is a dimensionless shear stress, of course, this is normalized by the shear modulus. If you put a constraint that the velocity and the displacements have to be, at least the material velocity and the material displacement has to be in the same direction as the remote velocity, you will get a bifurcation diagram like this. Okay. So the first sort of takeaway is in the electrodynamic equations, you do all this stuff that I just described, you will get two wave solutions that have detachments. So one will go this way and one will go this way. And both cause slip in the same direction. Just like the experiments, both cause slip in the same direction. The wave speed, so the inverse wave speed is plotted here, are symmetric. So in principle, both waves travel for a given tau r remote shear stress. Both waves travel at the same speed. Of course, as tau r approaches g, the linear elasticity assumption breaks down. And so this section of the curve is a little bit hypothetical, but nonetheless, you get two solutions of the equations. And each wave, as you saw in the experiments, contributes to a slip event. So interface is stationary, wave comes, interface jumps, stops again, wave comes, jumps again. And the theory also predicts the same thing. So if you have the plus wave, the remote velocity is like this, the wave is going from left to right, just like the applied velocity. And this is the slip, interface slip. This is the displacement. So the amount of slip moves towards the right. So the left region is slipped, right region is unslipped. This is the extent of the wave. And T naught is some non-dimensional time scale. And similarly for the other wave, you get the opposite. Now slip again is positive. Notice that ux by delta x is positive, it's not negative. So it slips in the same direction as V naught, but the slip starts occurring from the right end as opposed to the left end. Okay. So again, these two are symmetric solutions coming from the same electrodynamic model. And the slip occurs only during these wave motions. Otherwise, it remains stationary, as you can see here and here. Okay, now the big thing that came out of this, which is what led us to the actual second part of the work, is that if you look at the stress field at the tip of the crack, the tip of the wave, we have the displacement, so you can use Hooke's law and calculate the stresses. The stress field shows a divergence. So the region in between here is the crack, the wave, the plus wave or the minus wave, doesn't matter, both are identical. Ahead of the crack, ahead of the front edge and ahead of the back edge, you have a normal stress singularity, and you also get a divergence in the shear stress. Okay, and the nu equal to half is an analytical solution, which is green, and this also becomes singular, and the nu equal to 0.2, 0.35 and so on are numerically calculated, and they also appear to diverge as you come close to the crack tip, the wave tip. The interesting thing is that this exponent for nu equal to 0.5 is minus half. So the stress field looks exactly like what you would see ahead of a moving crack, right, for this pulse, which is maybe in hindsight a little bit intuitive, but then it seemed very unusual when we saw it first. Okay, so I'll summarize this part before I move on to the next one. So there are two types of waves, right? There's plus wave and minus waves. They have opposite directions of motion. and the slip that they affect is in the same direction. They have to slip in the direction which they're being pushed. They have distinct force signatures, and both travels at speeds much less than the Rayleigh wave speed. Right? The model, we get two wave solutions from the same elastrodynamic model. Singular limit in the wave speed, C by CL can't go to 0. C by CT can't go to 0. It's exactly solvable for the incompressible case. You do numerics for the compressible case, and then you can get the stress ahead of the tip and so on. And it looks like there is some crack type behavior at the tip of the wave, the front tip of the wave, right? Because the stress becomes singular. Yes. The applied velocity. The applied velocity is the only other scale in the problem. They don't exist. This is harmonic, right? The transients are all gone. There are no transients. If you think about it in this problem, the velocity scale is put in artificially, because we went to co-moving coordinates. We didn't talk about how the wave is nucleating and so on. So we force the velocity scale to be set by the displacement rate, right? So it's a little bit ad hoc in that sense. But nonetheless, if you do that, you will get this singular stress field at the tip of the crack. This is the prologue. Okay. Now the main question which I want to get to, with this as background, is why these fronts occur, right? And this is the result of some numerical calculations. The model is not very sophisticated. I'll go over that in detail. But before we do that, let's step back a bit and look at this friction fracture analogy a little bit more carefully, right? So let's say I have a body like this, and I want to push it from left to right. Okay. Assume the bottom body, the gray one, is rigid. Doesn't matter. Okay. Now, what's the difference between the one on the left and the one on the right? Right? The only difference between them is the boundary condition being applied on the top block happens on the left here, it happens on the top face in the right image. Right? Now, if you think about it, when the body starts to move, if you were to zoom in, let's say microscopically, let's say it's a very nice system, and there are no contaminants and so on, and you zoom in all the way at the end at the interface, the body will start to move when contacts start breaking at the static friction threshold. So when mu equal to mu s times n, when F equal to Fs equal to mu s times n, body starts sliding. Right? That's what we know from Coulomb friction. In the fracture problem, we know that when the stress, at least in LEFM, we know that the stress, when it reaches the critical stress, the Griffith stress, the mode 2 stress intensity factor reaches the critical mode 2 stress intensity factor, crack starts growing. So already you see that there is some type of loose analogy between the two cases. Now, it's important to understand, and we stepped back and thought about this a bit, about why these waves form, and we know that, okay, if they're propagating, we can describe how they propagate, but the application of the load should matter, right? So let's say I have three cases. I have one case where I push on the left edge, I have one case where I slide on the top edge, and I have one case where I pull from the right edge. Okay? If the body on top, the bottom body is always rigid. If the body on top was rigid, then all three cases are identical. It doesn't matter. Right? The net force will be on the right. If you're applying a displacement, the net displacement will be to the right, and it will be integrated over the entire. If you apply small amounts of displacement here and everywhere, it adds up. So for a rigid body, the three cases are absolutely identical. They're not analogous, they're identical, right? But if the top body is elastic, again, if you go back to that slip time scale that I was talking about earlier, and if you have significant elasticity in the body, then the onset to a slip is basically analogous to a crack nucleation problem. Again, this analogy is loose at this point. We'll make it a little bit clearer, hopefully, as we go along with some computations. Okay, and for the elastic case, you have to make a distinction between this, and this, because if the body is stationary just before it starts sliding, the stresses that are developed at the interface will vary from this case to this case to this case. Okay, it's understandable, and so the three cases should be different. So to look at where these onset events happen and what types of onset events happen and why they happen, we sort of resorted to a lattice model, and the idea again is very simple. I'll just give you the basic outline of what this lattice model does. So there are bulk bonds. So the bottom and the top are both elastic. We make the bottom pseudo rigid by increasing the stiffness significantly. The ratio of the stiffnesses are about 1:100. Each node has, it basically sits on a triangular lattice, and you have this type of connectivity, 60-degree bonds, and there is a normal stiffness and then there's a tangential stiffness. between each node, each pair of nodes. Okay, and you need both of these because you have to fit two elastic constants, the Young's modulus and the Poisson ratio. So this allows you to do that. Right? If you had just one spring, then the Poisson ratio will be fixed for a given Young's modulus and a given lattice orientation. Now we can fix both independently by changing these two parameters. Now at the interface we put so these are all bulk bonds. At the interface we put interface bonds, right? And the interface bonds are different from the bulk bonds because they are single springs and they have an initial rest length. The value of the rest length doesn't matter because it just decides how close or how far away these bodies are, and that determines the time step for the computation and so on, but it's a minor detail. But as the top nodes, the bottom nodes are all kept fixed, so the bottom rigid body is kept fixed, and as the top nodes move either up or left or to the right, these bonds stretch, and as the bonds stretch there is a restoring force which has components Fijx and Fijy, Ij being between the ith node and the jth node, and at some critical length, critical extension, the bond breaks. Okay, so that's how we simulate these contact breaking. It's a very simple model, but you will see that it gives very interesting results. So the equations we solve for are fairly straightforward. This is a completely linear system. We put in some damping to make sure that elastic waves don't amplify and the system doesn't become unstable. There are three force terms. There is of course what is called the bond force. This is called a bond model. Excuse me. And these are forces between neighbors on the ith particular node. This is an external force, so whether you apply a normal load at the top or sliding load or whatever, those come in here. And then there is the interface force. So this one doesn't apply to bonds in the bulk, it only applies to bonds at the interface. And we do three different things just to see what happens, right? It's a simple model, and the idea is simple. We apply velocity on the left. All the nodes on the left are pushed at constant velocity in the first case. We call this pushing. In the second case, all the nodes on the right are pulled at a constant speed. We call this pulling. And in the third case, all the nodes in the top face are given the same velocity. That's the boundary condition, right? Everywhere else, for instance, in this case, on this face and this face, stress-free boundary conditions. And the same thing with this face and the side faces in this case. Okay, and the entire system is solved for. Okay, now what happens when you push from the left? I'll play a video that shows you the color variation in the shear stress. Okay, this is the shear stress at every point inside the body, and you will see how it changes. So initially, for instance, at the right end, there is absolutely no increase in the shear stress, and at the left end, the shear stress goes up until the bond here is stretched beyond its breaking limit, it breaks, and then you have a nucleation event. And this continues. So you have the sequence of pulses that form and keep going from left to right. Okay, and time is non-dimensionalized using the Rayleigh wave speed. You can see that the propagation time is really small, right? It's 15 CR by L. CR by L tells you how long it will take for a Rayleigh wave to go through the interface, and this is much lesser than that because it reaches the other end only at TCR by L of 50 almost. Okay, there are a couple of things I'll point out and we'll quantify them on the next slide. The first is once the wave starts, once a little breaking wave starts, it keeps the stress field ahead of it the same, right? And the stress field propagates. And the same thing happens when the next wave comes, same thing happens when the next wave comes. That's point number one. The second is as these waves come to the other end of the contact, they suddenly start accelerating. So you see, for instance, that goes off, right? And the same thing happens to subsequent waves. As they come to the right end, they accelerate. These are the analog of the plus waves we saw earlier, right? The Shalamak waves that were going in the same direction with detachment. You can construct the same space-time diagram for this particular model. Again, these are all bond states. So you take the interface bond from x equal to 0 to x equal to L, and you stack their states as a function of time. So initially all the bonds are intact, then these bonds, for instance at this time, this bond breaks, and the bond breakage propagates as a pulse and goes all the way. The leading pulse, like I said, accelerates as it approaches the right end. Okay, that's a very curious feature that we observe, and this is irrespective of whether you have a large body, small body, big size, small size, doesn't matter. It seems to do the same thing every single time. And at the left end, these pulses nucleate at almost a constant frequency. So the time spacing between these waves is almost the same. So they are generated at a constant frequency, and they all go at a constant speed, right? And the speed, as you can see from the slope here, is much lesser than CR. So they move very slowly until they accelerate at the end. And the moment this guy accelerates the same time, and then it stops because guy is gone and continues, accelerates, the one behind it accelerates, continues, and so on. You can take the velocities and see what they scale with, right? This actually answers the question of what sets the velocity scale, because in the theory model we put in artificially that C by V naught was the actual scale, right? Velocity, applied velocity was the actual velocity scale. But now you see, if you plot this V by V naught as a function of various V naughts, again this is non-dimensionalized by CR, which is a constant, for over 2 orders of magnitude, the values don't change, right? Blue is the first front, orange is the second front, green is the third front, the third pulse. And the velocities scale exactly with V naught, which is consistent with what we assumed, but now it comes without any assumptions thrown into the model, right? The pushing velocity sets the scale for these waves, for these slow waves. Okay, now let's go back and revisit this stress ahead of the tip. So if you take sigma xy, again now I've non-dimensionalized it with rho CR square because it's a dynamic stress, there is a propagation happening, and the x-axis is plotted with respect to the x tip 1. X tip 1 is the tip of the first pulse as it's moving, right? That's always kept at the origin. So it's a moving coordinate system that is, the origin is at the tip of the first pulse as it keeps going. And you see that there is a sort of 1 by root r type of dependence. This dashed line is exponent half, minus half. It looks like there is a 1 by root r. And the trend seems to be consistent. This is at a later time after the second pulse is formed. So second pulse forms behind the first. Origin of this is again at 0, which is the first pulse location. This coordinate is co-moving with the pulse, right? And so the stress state ahead of the pulse doesn't change. Now at another subsequent time it remains the same, subsequent time it remains the same, even though other pulses are nucleated behind, right? So this 1 by root r type of thing appears to be robust as the wave keeps propagating. We can look at sigma yy, which becomes much more interesting. This also seems to be singular. Again, this is a finite lattice, so you can't say if it goes to infinity or not. It won't, because the forces in the bonds are, the finite distance between these bonds. And again, if you look at it in the co-moving frame, the stress falls off. This region is 0 basically because it's behind the wave where it's detached, just like here. The stress initially was very high when the first wave nucleated, but after that the normal stress is reasonably low, continues to be low, and the same thing happens with subsequent waves as well, right? Good. Now we go to the second case. If you pull from the right, what happens if you pull from the right? Now you have a wave going the other way. Okay, it starts at the right end, goes to the left, and it shows basically the same characteristics as the other wave, the plus wave that I showed you. And you see that these accelerate as you go to the left, they go keep their stress field ahead intact, and then the subsequent waves come with the same basic spacing between them. And of course the body has moved, right? The applied velocity has gone here, and the interface, you can see it started here, the body is moving, and the interface points are only moving when these waves go past them. So these two waves are analogous. So if I draw a space-time diagram for this opposite moving wave, the negative wave, you will get the same type of features again. Right? There's nothing different here. If you compare it with the one I just showed you, this is just looks like a mirror image of the other. Right? So pushing and pulling are analogous. The theory already showed us that there's this bifurcation symmetric diagram and so on. The numerics, where there are no assumptions, save for the model details of course, is also saying the same thing. So the nucleation also seems to favor both waves as being analogous to one another, going in opposite directions, causing slip in the same direction. There's just one more piece that confirms this analogy. So if you calculate the epsilon xx for a moving wave, you can show that the epsilon xx is compressive for the plus wave and tensile for the minus wave, and the sigma xx is basically the same, shows the same trend. One is compressive, other is tensile. Okay, now here is where things become very strange. So remember, we had these two waves going on like this, going in the same direction, detachment, blah blah blah. Now what happens if you shear it from the top, right? If you shear it from the top, there are two things. One is, this shearing is basically what you do in mode 2 fracture, right? It's the same configuration. There it's an applied load, here it's an applied velocity, but that difference notwithstanding, the configuration is the same as what is described in classical Westergaard solutions, right? The second thing is that the interface dynamics changes completely. So till now you had slow waves going this way and that way, wave speed was set by the pushing pulling wave speed. But now if you look at this problem, everywhere there is a build-up of shear stress, right? Everywhere in the material. And then at some point, the wave is gone. Let me pause it. It's building up, building up. There's a front that starts at the left, it's gone. Okay? Building up, building up, building up, building up. Breaks, it's gone. Right? And there is some rebonding that happens because there is rebonding in the model to allow for reattachment of the interface, but that happens much after the interface wave is gone. Right? The rupture front is gone. And that basically is like a shear crack. Right? It looks at least like a shear crack. And it travels very fast. It reaches the Rayleigh wave speed. If you look at the space-time diagram, it's basically flat, right? The height between these two is 1. So TCR by L is 1, which means T is L by CR, right? Which is the time taken for a Rayleigh wave to go. This is the generalized Rayleigh wave speed. It's not the exact Rayleigh wave speed, but nonetheless. Now, there is obviously some rebonding that happens in the model, but that's all subsequent after the wave has gone off. And if you compare this with the other diagrams I've been showing you, you will see the distinction is extremely stark, right, between these two cases. If you calculate the velocity, you will see that this velocity of the front scales with CR. For various values of V naught, you will get the same result, right? Irrespective of how fast or slow you shear on top, the front will always go to the Rayleigh wave speed. This banding you see is a numerical artifact on how the wave speed is calculated in front, but it actually reaches 1. Okay. Okay, let's look at the shear stress side of the crack. There is also a singularity that comes here, but this is where the thing becomes a little bit murky. So this again, co-moving frames. Now there's only one tip. There are no pulses. There's just one crack tip. So that's the one that's kept at the origin. And you look at the shear stress. The shear stress builds up as a function of time. These colors are all at different snapshots of time, and you see that it remains high. The normal stress falls off again for a dynamic crack moving like this. Right? This is consistent with what you would expect for a dynamically moving shear crack at the interface. Now, the experiments I showed you didn't reveal this particular Rayleigh wave speed crack. Right? They showed you two waves going opposite direction, both had detachment and so on. But if you probe reasonably carefully and you play around with the parameters a bit, you can, within quotes, see the other wave. Now there's no detachment, so you have to put cross polarizers and do photoelasticity and recover the stress field, but you can see the signature of that in the experiments. Excuse me. So I'll show you one quick video. This is an experimental video, again looking at the same contact interface from before, but a narrow region in the middle, and the color is loosely proportional to the shear stress at the interface, right? It's actually proportional to the difference in the principal stress, but okay, that's approximately equal to the shear stress because the normal load is very low. And blue is low shear stress, red is very high shear stress, and look at these 2 points, right? Again, you're moving from left to right. There are 2 points that will appear behind these red dots, and then they'll get shifted to the green dots as the wavefront comes. So the interface stress builds up, and then a pulse goes through, right? And this travels at a much higher speed compared to the other 2 pulses. And you can't see this travel because there's no detachment, no significant detachment associated with this particular wave. Okay, so I'll maybe sort of ease off here with some analogies, because I think this leads us to a lot of other interesting domains that perhaps at first sight look completely unrelated. If you look at how a caterpillar moves, it's basically a long elastic body, just like in the lattice, and it's moving on a rigid ground whose modulus is much higher than the elastic body, and it moves by creating these locomotory waves. So you can see a wave going from the tail of the caterpillar, which is here, all the way to its head, right? And when the wave goes, the thing moves, right? You can see that one more wave is coming in. These are slow waves because that's not moving at the Rayleigh wave speed. You can see similar waves in a very different context. This is what is called peristaltic motion in what is called a planarium. I'm not a biologist, but I hope I've got the term right. And they move by doing the same type of motion. They create these waves that go from tail to head or head to tail. Right? And if you dig up some of this literature, is actually fascinating because there are lots of very interesting studies people have done in this community. Here is one by a person called Gray, who has a famous book called Animal Locomotion. And he basically put some of these insects on a glass slide and looked at them from below and then figured out what types of wave motions you can get. And he found that there are two types of waves. One goes plus, one goes minus, right? It's a moving elastic body on a frictional substrate, and it moves by these types of wave propagation. And there is another wave in this caterpillars, which is called loping locomotion, which basically has a detachment that forms and goes all the way to the head. So for instance, this is the head, this is the tail. It forms a little loop. These gray segments are off, they're detached, and that loop goes all the way to the head, and the head jumps by delta of how much ever is formed here, right? This is the step length. And so you see some of these analogs in the insect world, which appear to have similar types of features, at least. Maybe dynamics might be different, but they're also elastic, and they're also adhesive contacts, and they have rigid substrates, right? So we think there might be something worth studying in this context of these moving waves. So I'll quickly summarize our basic findings. Again, there are lots of questions that are sort of open, which we're still trying to think about. The first thing that is absolutely certain is that the way the boundary conditions are applied makes a big difference, right? And this is something that I think a lot of people have sort of neglected. Perhaps one reason for that is many of these frictional models are one-dimensional, where you can't apply boundary conditions on the top face, like Burridge-Knopf models, and many of their derivatives are one-dimensional. And so this perhaps slipped through the cracks, if I can use that phrase. But it makes a big difference in what type of wave you can get. Now this begs a question, can you postulate a criterion for slip initiation, right? Now, just like I said, the criterion for crack nucleation is a far tougher problem than the criterion for crack growth, right? If you have an incipient crack, you can say under what loading the crack will grow. But given a loading with there's no crack inside the material, predicting when a crack will form is not very easy to do. And so can you use something like this to give an analogous explanation for slip initiation, which is basically the same problem. The stress intensity factors, there is a technical problem. Again, I didn't want to get into these details, but for interface cracks, if you have worked out details for moving interface shear cracks, you will often see that the stress intensity factor has a complex exponent, right? And that is problematic because it gives something called an oscillatory stress ahead of the crack tip, which is unphysical because it leads to things penetrating and so on. That comes up in our model as well, the theoretical model. We think that the numerics, the lattice model, doesn't have that artifact, so we hope that we can extract some type of process zone type of interpretation from the lattice model and try to see if we can go back and correct, just like the Dugdale solution for shear cracks, if you've seen it, something like that for the original solution. And like I said, there are many other interesting problems that seem to have the same type of features, which is something that we've been thinking about a bit. The other couple of things we've been thinking about is when you look at this shear crack going in the top loading case, that's more like a brittle mode for the material to move in this case, versus a pulse going at the interface is more like a ductile mode for the material to move. So can we use some analogies between ductile to brittle transitions for explaining some of these transitions is another idea we've been playing around with. With that, I'll stop here. Some of this work was funded by grants from SERB and DST, and these are the guys. So this is actually at a outreach event called Open Day at ISE. In case some of you are in Bangalore or plan to go to Bangalore next year, the last week of February, the last Saturday, we open the institute out to everybody. It's free. There'll be a huge crowd, but we have demos that we do and so on. That's a small lathe that we built 3 days before the actual event, and this box had a demo with Rupert's drops. I don't know if people have heard of Prince Rupert's drops. we got a LPG gas cylinder and made them in our lab the previous night. These are small tadpole shaped glass drops, and you can hit the head with a hammer, it won't break. But then if you just slip the tail, the whole thing will explode. Right? And we were just doing some of those demos for high school children and things like that. So yeah, thank you so much.
Thank you. Thank you very much for this interesting talk. We have some time for questions, comments. Please.
Yeah, Kaushik, it's a fascinating talk, and there are many takeaways. There are many conceptual clarity that I also got. So I wonder your last remark you just made, due to two different loading configurations. So I wonder if there is a side loading, and you wait long enough, or your body is large in size enough. Does that transition to what similarly that you observe for on top loading?
That's a good point. We tried that, it doesn't.
It never.
No, and one of the reasons why this moving object looks so long is to test something like that, and it doesn't seem to happen.
Okay.
Because the nucleation criterion is a very local criterion, and when you top load in shear, right, you top load the body, the stress field is uniformly distributed for the most part, and so the breaking happens. So the strain energy that is stored in the material is extremely high by the time nucleation happens. That's our loose interpretation. Some of the quantification is not here, it's in the archive paper. So that's the loose interpretation, right? The elastic energy that's stored in the material at the time of crack onset is extremely large in the top loading case because the stress field is like that. Whereas if you do the side loading, the localized stress state near the tip is where all the strain energy is, and that's much smaller than the other case, which is why we also think the first case it accelerates very fast compared to the second case.
Okay.
Because the energy release rate is much higher. Yeah.
Yeah. So is there? Yeah. That actually brings to few series of questions. So if I may, so there are two things. First, do you incorporate any interfacial law that you mentioned at the onset of the talk, rate state? Is there something there?
There is just a breaking law for the interfacial bonds.
What's that?
It's just maximum stretch. So we predetermine delta L for the springs.
So there is no interfacial stress and slip relation?
No, there is a bond. So the top body has a lattice, bottom body has a lattice. The nodes that are closest to each other are connected by bonds initially. And these bonds will break when the length exceeds some critical length.
Right.
And the delta L at which it breaks is the only parameter you need. The absolute value of the rest length doesn't matter so much. So, and we also have a reforming law, which is when the velocity of a node becomes lesser than some value within some tolerance, and the distance becomes small enough, it reattaches. So there is adhesion explicitly also put in.
Okay.
Otherwise you won't get reattachment.
Yeah, so this is like a frictional healing.
It is a frictional healing law. Yes, microscopic frictional healing law. Yes.
Okay. And so because you have all the quantities ready, strains, the stresses. So did you try calculating exact energy release rate that each time the bulk sends into that crack, and whether there is a critical, but I think hard part may be to quantify the fracture energy at the interface.
That is the problem. That's exactly the problem. Yes.
Okay.
We have calculated the energy release rate. Like I said, loosely it's higher in the sliding case and lower in the other two cases because the strain field is localized near the tip. But calculating the adhesive energy is not easy.
Okay.
Right?
Yeah.
So,
thanks. Fascinating talk again.
thank you.
Thanks very much. Other questions or comments that you would like to address, please?
Constant emission of slip pulses with some periodicity. Does that also depend just on your macroscopic velocity? Or
It does. It does, yes. I didn't present the scaling of that frequency with the applied velocity, but it does. The loose sort of back of the envelope explanation I can give is if you have n of those pulses at the interface, then the slip caused by n of them in time delta t must be equal to V naught delta t, because the total interface slip, total slip remote should match up at some point, right? That's loosely, so n scales as V naught.
Yeah, but you could have spacing that is smaller but jumps that are larger.
That is something we have not yet explored actually, because there it becomes critical what you set the breaking load to be and what you set your readhesion condition to be, because that will determine the width of the pulse. And once you set the width of the pulse, the next pulse will nucleate only when the stress goes up significantly for a bond to break. So there is some muddying that happens with the interface law for that particular relation. We're still sort of trying to segregate them out.
Thank you.
Thank you very much. Any other person wants to participate? If not, we should thank the speaker again.
Thank you.
Thank you. And welcome our next speaker of this afternoon session. So our next speaker is Mrs. Tapati Dutta, who comes from St. Xavier's, Kolkata. And the title of her talk is Self-Organization of Evolving Cracks Towards Voronoi-ness.
Let me first thank the organizers for inviting me to my first Fracmeet and for the very generous hospitality they have been extending from the very minute I've stepped into this beautiful city. I know it's the fag end of the day, but it has been a day of beautiful talks, and I don't know how I will measure up to it, but my talk is self-organization of evolving cracks towards Voronoi-ness. Now, the key words here are to note are these self-organization, evolving cracks. So we are talking about cracks that are growing, and what is Voronoi-ness has been lightly touched upon by some of the speakers. I will speak of it at greater length at the right time. So there already exists a large body of literature on the formation and propagation of cracks and crack networks in connection to fluid transport. We heard a very beautiful exposition of it from Professor Alex Hansen. And then there are scaling laws in fracture interfaces and mechanisms of failure. And we have heard very, very beautiful talks on these areas. But there are certain mathematical aspects of crack networks that we feel in our group that also need to be looked at. So for example, when you look at a crack network, for example, this is a mud crack. This is a crack network on a stone. This is on glass. This is on painting. And this is a shari, which is again a crack. It has been printed by what we call in India batik print. That is, it is coated with wax, and then the wax is cracked, and you dip the fabric with the cracked wax in different colors, and you get these, their cracks act as templates. So they all crack, the crack networks look different. So the point is, we wanted to, how would you classify a crack network? One could speak of topology, which speaks of connectedness of the crack network, and you could sort of encapsulate it in what we call a NV combinatoric. What is N? So if there is a node in a crack mosaic, then the vertex of N polygonal cells or crack beds, then that node is said to be of degree N and is termed regular. I will explain. Say, for example, if you look at this here, can you see my cursor? This is the cursor. I don't know. Cursor cannot be. How do you show the cursor? Which one do I press? All right. So if you look at this node, for example, this is a node to 4 regular polygons. So I will say this has a degree 4. This is also a regular polygon, but if I look at a node here, this is again a vertex of 6 polygons. So this is of degree 6. But you can have irregular nodes too. For example, this node here is the vertex of these 2 polygons, but not of this. So I will say it has a degree 2 as because this is an irregular and this is an irregular node. Similarly, look at this node here. This is also irregular in the sense it is shared by 3 regular polygons, but not this. So it has a degree n. So that is the way we assign n to a node, the degree n. What is V? Simple words, V is the number of edges to a polygon. So you can talk of any crack network in terms of this NV combinatoric. And you can also define a regularity index P, which is a ratio of the number of regular nodes like here to the total number of nodes. All right? So these are basic definitions. Now, in most convex polygonal crack meshes, you will find NV values ranging from 2, 4, that is n is 2 and V is 4, to 4, 4, and depending on whether the nodes are regular or irregular. A 2, 4 topological description of a crack mesh is the signature of a Gilbert tessellation algorithm, and they are referred to as Gilbert cracks. Whereas on a triangular lattice, what we saw is a 3-6 combinatoric. The node was of degree 3 and it shared 6 polygons. So this 3-6 combinatoric is usually typical of a Voronoi tessellation and is referred to as Voronoi cracks. So you can combine the regularity index and n and v to write an algebraic equation like this, and you can draw a NV domain in which all crack meshes can lie. For example, P has to be 0 and P is equal to 1. This is one boundary. And for all closed polygonal meshes, the least you can have is v equal to 3, and you can go up to v equal to 2n. And this pink area is therefore the NV domain in which all our crack meshes should have their NV values. So for example, this is a 2, 4 index, and for that you would have an irregular crack mesh looking like this with 2 here and 4 sides. This would correspond to a 4, 4 value, which would look like a crack mesh like this. And this would be a 3, 6 value, and this is your Voronoi cracks. So our aim was to study all the crack networks that we see normally and see if we calculate their NV value, where do they lie on that domain? The motivation was that, say for example, clays, if clays of the same family have their NV in the same place? Do glass have their NV in somewhere else? So do materials show some signature belonging to a particular class in the NV domain? That was what we were looking for. So we studied various cracks, real and simulated. This is just an example of real cracks we did in a laboratory. This is lapunite cracking under 2 different pH values. So finding their NV is a bit more complicated. You have to grayscale them, and then you have to find out their skeleton in a manner like this. So let's say this is the skeleton, then you have to count the nodes and you have to count the vertices. And but all this is only valid for convex polygonal cracks. If sometimes there are concave ones, and then it becomes a real problem, and we had to develop absolutely indigenous programs. All of this we did, we had to develop our own programs to sort that out. And then of course there are the simulated cracks. These are all Gilbert crack tessellations of different distributions as regards their geometry. This crack is also simulated, but through what is called an iterative cell division, which is basically very simple. You take a cell, you take any two random points on two opposite sides, you join them by a line, you get two compartments. Again, you take for each of the compartments two points on two opposite sides, and again join them, and you keep on repeating it, and after several steps you can see you get a crack system which is fractal. This is a Voronoi crack. Again, it was generated by us, and this is a random distribution of Voronoi cracks. This has a Gaussian distribution. But when we did all of these and we put them on that when we put all of this and put them on this when we put it on, when we put it on this NV diagram, we saw that the cracks sort of all lay in this value between 2 and 3, and there was only one Voronoi which had a 3,6 value. All the other cracks, you can see Gilbert, Voronoi cell division, bentonite, laponite, starch, PDMS, which is a polymer. Then we did some oxides, tempered glass, resin, mud. So we actually looked through all of these crack networks, and we plotted their NV values and found them, most of them crowded like this. And there is, at this time, there was also a work by Domukos and his group, and he called this this plane, he called it a platonic attractor, saying that most of the geological cracks also had an NV value here. But we were not happy because the cracks look different, right? When we looked at the cracks, they do look different, but we couldn't differentiate them from this. So they're not well reflected here. So we thought that it is not enough, and mere topological description is inadequate. So what we did was we introduced geometric description. So we defined something called the angular defect. So what's that? So if it is a regular quadrilateral, we expect it to be 90, but a quadrilateral will have 4 different angles, and each angle could be different. Let's call each of them theta I. So how much is theta I different from 90 in this case? So this you can do for any polygon, and that is when averaged over the entire mesh, you can come to some D average, which we call the angular defect. Also, we introduced something called a shape parameter, which is called the isoperimetric ratio. This is often used by mathematicians, and you can see defined like this, where A is the area of the polygon and L is the length. In this case, it's the perimeter. So defined like this, you can see that lambda will be 1 for a circle, and it will be less than 1 for other polygons. And if you have needle-shaped polygons, then very sharp, like shards of glass, then lambda is going to be very small. So in a layman's language, we may say that lambda is a measure of the roundedness or the geometry of the crack. So then we wanted to describe the polygonal crack meshes in terms of a 4-tupule, that is n and v were already there, and we introduced d and lambda, that is the geometric factors, but we can't plot all the 4 in one diagram. So this is an NVD diagram, and if you just look at how the d values differ, you can see that for all those cases that we studied, the d values are now a little bit more separated. And we did the same for the NV now lambda space, and we see that the lambdas are again not as well separated as in D, but still quite separated. And we said that, okay, the topology geometry combinatory described via a 4-tupule NVD lambda is necessary to differentiate crack mosaics of different materials. This work was published in Physical Review E, but at that same time, see, this is the vast allowed domain, all right, of crack meshes. And yet, when we looked at it, we remembered by that time we had seen columnar joints. Many of you would have seen columnar joints, and their crack mesh, if you look at a transverse section of it, is very, very hexagonal. So that means they have a NV of 3,6, and that would lie somewhere right up in one corner, whereas all the others are all clustered around somewhere else as far as their NV is concerned. But geologists say that these columnar joints at one point of time started off as random cracks. That means once upon a time they were clustered in that group, and somehow over geological time they had moved to that Voronoi point there. So that got us interested to finding out what is the trace of the path they would have followed and why. So these are pictures of columnar joints. This was actually, these are in Genbudo Geopark in Japan, and these are what they look like, and this is what they look like if you cut them across like this. You can see a very, very regular hexagonal shape like this. So we wanted to study columnar joints. So how are columnar joints formed? So they are formed from cooling lava. So when lava cools, say for example this is a schematic, this was lava, let's say, and as it comes in contact with air, it cools and it starts cracking to release its thermal stress, and you get random cracks like this. But now what I am showing here is a longitudinal section of how the lava, how the cracks propagate in the vertical direction to ultimately form the columns. So what you see here is this crack front, this crack tip here is represented like a conduit here, and the ped size here is basically a column of uncracked ped rock piece. And again you have another crack front, so this is it. So what you see in this longitudinal section is like cracks which tessellate the surface into columns of different widths. Now what happens when a crack is formed? Then the cold air from outside enters. First of all, there is cooling happening here, and then cold air also enters the crack, and it starts cooling these columns from the sides, from their interfaces. And you know, the hot air from above goes up. So in these you have convection currents. And these masses of molten lava, they cool not only from the top surface, but as the crack front has air circulating it, they cool also from across the crack faces in this direction via conduction. So there is cooling by conduction and convection. However, depending on the width of the crack, you can see that a thicker, fatter crack column will have a higher temperature in its center than a thinner column. So the point we are looking here is that there is no reason to assume that one crack will, you know, unless if I assume that they are all homogeneous in the transverse plane, there is no reason to assume that one crack will propagate more than the other. So we can assume that they are all propagating at the same plane here. And the question here is, in our next time step, let's say, where will this crack move? Will it move straight down, or will it change its direction? So that is decided by the isothermal lines here. So the isothermal lines, because of this unequal temperature distribution between the fat columns and the thin columns, the density of the isotherms here at the face of the crack columns here is different. And this particular crack node is therefore acted upon by the thermal stresses of its neighboring columns, and it's going in a next moment of its movement, it is obviously going to move in a direction in which it can release its thermal stress most easily, and that will be in the direction of the steepest gradient of temperature. So if there is greater crowding here, this crack, instead of moving down like this, will change its direction. So in effect what happens, so we are looking at this mechanism which enables a crack which could have been, which started as random, ultimately how can it change its shape and become hexagonal. So that's what we are looking at. So we simulated it like this. So let's say this is a crack node, all right, which is shared by the adjacent columns like this, and each column exerts its thermal stress, so that this node actually is, its movement is going to be decided by the resultant effect of the thermal stresses of all the neighboring polygons with which it shares itself. So let us say that we don't know which are the centers of the thermal centers, heat centers of these pillars, but let us assume that they are the centroids. And so we take the distance connecting the centroid to the node as di, where I runs over each of the neighboring columns, and then we say that in a particular time the amount of movement that this node will make in, let's say, a direction dn, where dn is some I, will be some fraction of dn. So what is that fraction? That fraction is some correlation function where you can see d average is the average of all the d distances of all the di's, and therefore that takes care of the neighbors, all the neighboring polygons, and d max is the maximum length here, and it is written in such a way that when d max is equal to d average, you can see that this will become 0, and therefore there will be no further delta x, and that means in the next and next time steps it's just going to move straight vertically down. So how does it look like? Yes? Oh my God. So how does it look like? I don't know, it's not playing here. I had this, I don't know why is the movie not playing. So, oh, is it? It's not playing on the board. How does one play it here? I'm so sorry. How does one play it? I don't know. What's in here? Oh, you can see it playing anyway. So this is the node which is moving that way. And I don't know, I'll just click it here, and you can see that what was irregular is now slowly changing its shape to the polygonal, the hexagonal things. All right. So next what we do is we come to what we had simulated. So these are our simulated columnar joints, which look very similar to what we see in nature, and we picked out single columns to show that what began as a different shape ultimately grows into a hexagonal thing like this. So all this was fine, and our journey to answer our question that how does it move on the NVD diagram. So if you start from here, it reaches the Voronoi point, we saw like this. What was important to note was that the area distribution does not change with time. These are time steps. However, the theta, the average angle of the polygons, they changed and maxed around 120 degrees. That is, they are becoming more and more Voronoi-like. So the point is, if they are going to be more Voronoi-like, one would expect that they want to do that, and that would mean there is some kind of energy minimization. So we take a little section of it and assume that it is moving, penetrating a distance dz in time dt. So what could be the total energy contribution? We say that there is an elastic energy, and E0 here is everything else apart from elastic energy and fracture energy. There could be other contributions to energy, so let's call that E0. This is elastic energy. You can see that this is the volume of any particular PED, okay, where dz is the depth of it, and therefore gamma is elastic energy per unit volume. And fracture energy, that means to open up a face, you just calculate what is the total length times dz is the total amount of fracture space opened up, and eta is the fracture energy per unit area, and therefore as per unit length you can write the energy functional like this, right in terms of lambda, our shape parameter, because it was defined like this. So having done that, we actually, our simulation enabled us to plot L for every time step of the entire mesh and lambda for the entire mesh, and we saw that it followed a power law like this, and when we put it into the energy expression, we ultimately found that the energy follows a law with lambda in this manner, where alpha and beta we could 3 here, and lambda, the shape parameter for our mature rocks, was 0.75. What do we say, mature network? When the shapes don't change anymore. So when you plotted E versus T following this, we got this curve, which actually another group, Jagla et al., they had done these similar things, but they had worked with Monte Carlo simulations, not taking into factor the actual mechanism. That's what we thought. So now I come to the other point, which is Voronoi-ness, which we had spoken of. Voronoi patterns are very often seen. You can see this is in this is permafrost, this one. This is dragonfly, and this is Voronoi pattern seen in Mars. So the point is, Voronoi diagram, somebody mentioned, I think, that it is what is so great about Voronoi diagrams, that if you have a seed, every Voronoi diagram has a seed. It could be a seed of thermal stress, of moisture, highest moisture content. It could also be the center of mass. But all the space inside that polygon is, all points inside that polygon is closest to its own seed rather than to any of the other seeds. Voronoi diagrams are really fascinating, you know. If you're a football fan, I'll just take 1 minute because I was so engrossed. Like, you know, I really saw that Barcelona and all that, they are great fans of football. So their managers, they take drones and took, you know, pictures, movie pictures of how Messi and all they play. And in the football field, the 11 players are playing in such a way that the field is entirely always divided into a Voronoi-like pattern, with each of the 11 players acting as seeds, so that the field is sort of covered all the time, you know. So apart from that, it is used in many things. Basically, it is an optimization of some quantity, whether it is space, whether it is energy. So Voronoi diagrams are very important. How do you generate Voronoi diagrams? So you take some random seeds, and you do a Delanoy tessellation of it. Delanoy triangles are duals to Voronoi triangles, and then after you do the Delanoy triangles, you draw circumcircles, and then you take the centroids of it, and then you simply join those centroids which share an edge of the Voronoi triangle, and what you get is a Voronoi diagram like this. So that's all right, but what about real cracks? So for real cracks, we did a skeleton of it. We took the centroid of those polygons because we really don't know which is the seed. And then we did the Delanoy triangulation, and we did the circumcircles, and these are some of the real cracks that we worked with. And you can see here that some of the Delanoy, you know, circumcircles are marked in red. Why? Because this is not a perfect Voronoi, as because in a perfect Delanoy triangulation, it should not contain any other seed. those that contain a seed, they have been marked with red. So you can define how good a Voronoi diagram is by defining something, the number of non-empty circumcircles divided by the total number of triangles. However, look here, this mud crack and this honeycomb, both are, according to this, they are perfect Voronois, but they are not equal. So what we did was, the question comes, how good is a crack to a perfect Voronoi, or how much is it deviated from a Voronoi? So in mathematics, there is a Hausdorff metric which is defined, which if you have two sets of points which belong to two meshes, let's say A and B, you can start by drawing lines between A and B and finding out what is the biggest length between them. So here you have ds, and you can do the same for going from B to A, and you get here the largest length is D11. So the bigger of D6 and D11 is your Hausdorff metric. So we calculated our Hausdorff metric, and in terms of pixels, the mud crack was 14 pixels. That means if the Hausdorff metric is 0, it's a perfect centroidal Voronoi. This is not a perfect centroidal Voronoi, but it goes to Voronoi-like tessellation. Just, I will very briefly, if you give me 3 minutes, I'll complete the talk here.
Sure. You are consuming your time for questions. It's your choice.
Just
3 minutes.
I will just take this example of wetting and drying cycles that Lucas and his group had reported long back, where they had said that if you repeat on mud cracks cyclic wetting and drying, then T junctions gradually change into 120 degrees at the junction points. So we did something very similar to this columnar joints, except here what's happening, it is instead of thermal stress. So when you have drying, there is desiccation, and the center of the beds are points of highest moisture content. And so there is desiccation cracks, and we did a spring network to show that the node is as if related to all the polygons it shares with a spring which has a natural length d0, and every time there is a drawing, it shrinks by a certain amount. N is a time step, so how much it shrinks is determined by its value of the spring at its previous time step. And when you wet it, what happens? It swells, it relaxes a bit, and it goes like this. And the amount was calculated and all that, so this is not important. And we again found that the energy decreases with time. So, and not only that, before you could start the wetting drying cycles, they look like this, the stress distribution was like this, and after repeated wetting drying, they took this Voronoi shape and the stress distribution became like this. So this is what I wanted to tell you. And once again, we calculated the Voronoi, we wanted to see how good a Voronoi they were, and obviously there were some, at the beginning they were more red, and certainly they were less red after that. And we plotted the P and the Hausdorff metric. You can see that it is certainly going towards Voronoiness as the values are falling. So what, this is not important. There are some other laws for which are existent for polygonal meshes. Our simulation could reproduce them. This is also a paper by Ruhul in Chaos and Solitones and Fractals. And so this is another work, another example, but this is completely different. This is another system, salt pliers. You would have seen Ruhul has a poster on it. Ruhul is my scholar, by the way. And so what is the takeaway? It seems that dynamical crack mosaics tend to form Voronoi-like polygonal mosaics in equilibrium in order to optimize some property. In our case, it is probably elastic energy. And with this, I wish to thank my collaborators. This is basically all work done by Ruhul Haq. He is here in the audience. Atish Mitro is our mathematician in the group. He works in Montana Tech in USA. Anamika Roy, some of you have met. She's also one of my PhD scholars. Shujata Tarafdar is like a touchstone for us. Everything we do or say, even if she's not actively involved anymore, we share with her. And I'd like to thank you for your great patience. Thank you.
Thank you very much. Thank you. Thank you for this inspiring talk. I'm afraid that we won't have time for any questions, but of course, I'm sure you will be happy to answer questions during coffee breaks and dinner. We have to move to our next speaker. Thank you again. And our next speaker, thank you again for this nice talk. Besides Messi, I could orient you towards Gaudi architecture and his basaltic columns, which are very, very much reminding of the shapes you showed us and the evolutions. Thank you. So our next talk and last talk of this afternoon session is from Marcel Moura, Porlab in Norway. He will be talking about experiments on transient and steady state flows in porous media, the transition from viscous fingers to compact displacement during unstable drainage flows.
So, good. Thank you, Jordi. Thank you very much again. I shared the words from the previous speakers. I want to thank the organizers and been having a very good time here. Your hospitality and kindness since the minute I arrived here. I'm very happy with it. This is a very long and bad title that no one will remember, but I'll be talking about experiments, I'll be talking about transient flows, and I'll be talking about steady state flows. And I work at the Porlab at the University of Oslo, and this work is done with a bunch of people in the group of Knut Jørgen Molloy there. Okay, so here you have a little video of an experiment. I'll be talking more about that later on. So there will be two parts in the talk. The first one is transient, the second one is steady state. And what you see here is injection of air, in this case, into a porous medium that is filled with another liquid. It's a liquid that's more viscous than air, so that's why you get viscous fingering like that. This is what this type of behavior is called. And on the second part is the co-injection of two liquids that do not mix. That's the kind of thing that Alex has shown a little bit before. And since I'm the last speaker, I'll try to grab your attention. So this is a little bit of eye candy here. These are birds. I do not study birds, but I think these are very interesting. I don't know if anyone has seen one of these things here, this big cloud of birds. It's called a murmuration. And it's a very interesting type of collective behavior. You see, like here, there's a predator that's flying around and is trying to catch the birds. And the whole thing kind of like behaves as a single organism. You know, you can see like some waves, propagation, like information waves that go around this thing. I could show this the whole day. It's really interesting. This one here, I don't know where the predator is. It's somewhere there. Oh, there it is, up there. And then it tries to capture them, and then you see like these waves that kind of like tells to the other organism, there is something here, so move away. And the point here is, even if we know everything about one single entity of a system, it doesn't mean that you immediately know what happens when you put a bunch of them together, because complexity arises, and a lot of the things that we deal with has to do with this kind of general idea that when you have like the collective interaction of many particles, whether it's flowing porous media or fracture propagation or anything, new things appear when you try to scale things up. So going from a smaller scale to a larger one is often not easy, and this is also true in porous media. Upscaling is pretty hard, and there's a lot of us trying to understand these things. So this is the pore scale where we understand the physics pretty well. So this is where classical fluid mechanics applies. So Navier-Stokes equations, basically, for Newtonian liquids. And then to go from here to here, the core scale, the type of scale of samples that people take to study porous materials is already a tremendous job. And then going from there to this scale here, the aquifer scale, this is the Guarani aquifer in South America. there is enough water there to feed the whole world population for something between 200 years to 1,000 years, depending on what kind of like a model for the growth of population you use. So these things are very hard. The experiments that I'm going to be showing are somewhere between these two scales here. And okay, so let's go to the first part about transient flows. And the easiest transient flow, the easiest drainage experiment that we have, we can make it here. If you take a little tea bag outside and you put it on top of a napkin, what you see is a drainage experiment where air enters from the sides here in a big succession of bursts. These bursts are what we call Hayne jumps in porous media, and it's a very characteristic thing of a drainage. That's when you have a non-wetting phase entering a porous medium that is filled with a wetting phase. So for instance, air entering a material that has water inside. So that's this case here. And people have studied this a lot. So here is a little model that we have. It's a single layer of beads, of glass beads. And then if you inject air fast, you get this type of pattern here. It's called a viscous fingering pattern. And if you do the same thing, you just change the injection speed. So I think here is 4 times slower injection speed. You see that the pattern changed a little bit. Now you have like these trapped zones here. I think that's related to one of the questions that you had in one of the previous talks. So this trapped clusters here. So if you have a deformable porous medium, so this is an experiment where you have like a grains in a suspension in between 2 plates. And then the grains are what you see yellow there. And then you suck out the liquid from the center. So air enters from the sides. You got this type of a structure here. This is called a frictional finger. And people have studied all this type of different regimes. So what happens here is, since the grains now can move, they are not stuck in place. So suddenly frictional forces are important again. Are important now. And people have studied these things and made the phase diagrams like these ones here. You see, if you change, for instance, basically what you have is like you have a bunch of parameters. You change that parameter, you see what happens with the pattern, and then you try to understand why that is happening. So here, if you go from slower to faster, it's in this axis, and in this axis is more deformable or less deformable. So here, the porous material is fixed in place. Only the fluids can move. And here is what happens if the porous material itself can move. And different groups have studied this system on varying different types of things. So here is if you vary the wettability of the medium. It was done by the group of Ruben Juanes in MIT. And here, so what we'll be talking about, the work was inspired on this work here by the group of Bischoff-Berger. And she has been studying what happens if we inject the one fluid into a helical cell. That's just 2 glass plates that's filled with another fluid. And then you change the viscosity ratio. So basically you make you increase the viscosity of the fluid that is entering, or I think she decreased the viscosity of the fluid that's around. But anyway, what matters is the ratio. And what she found is that you go through a transition between the usual viscous fingering type of instability, that's this one here, Safman-Taylor type of instability, that's well known, to something where you have a central zone that's compact with fingers on the outside if you increase this viscosity ratio. So here there is no porous medium and the fluids are miscible, and then we ask the question, what happens if we have immiscible fluids and a porous medium? Okay, so these are the experiments. So for this experiment here, we are keeping the pressure of air. Air is what's entering from the center, it's what's white in the image. So we keep that pressure constant, and then we vary this viscosity ratio. So we basically decrease the viscosity of the liquid that's there, of the darker one here. This is the usual viscous fingering pattern. And then as you increase that viscosity ratio, you start to see different things like this one. And here, very fast, something that looks completely different from that. And what you see is you start to see something somewhat similar to that you have like a zone closer to the center that's more compact, and then you have fingers around that perimeter there. So we saw something similar, and then this was published in Physical Review Fluids, and we tried to understand this type of regime here. And that is what we call a compact displacement regime in contrast with the viscous fingering regime here. This is what the model looks like. So it's about 40 centimeters in diameter. So this is not microfluidics. This is centimeter scale type of experiments. And we have a bunch of pressure sensors that we put around here. So here I think we use the 5 or 6 so that we can have an idea of the pressure field as well in the experiments. So if you, the 3 experiments that I showed you are these 3 here. And then if we change the injection pressure, we can populate this phase diagram here. This regime here, this is what's called capillary fingering. So that's the domain where capillary forces are important. Things are very slow, and then basically the force of surface tension is what's governing the dynamics there. And this is the usual viscous fingering case around here. And then if you move that way in this diagram, top left, you have this domain here where you have this compact invasion. So we digitize the image and we make this, call it invading matrix. So this is just this colorful map here. It's very convenient because with just one image, we have access to the temporal dynamics. The color is just the time that a given pore is invaded by air. So it's this kind of like a way to get like a video in a frame, the information of a video in a single frame. And we do the same thing for here, and that's what the type of map that you get. And you can see already from this that you got this type of more circular invasion here, also in time, and the usual fingering structures on this part of the diagram. And we do this, there are 23 experiments that were done here. And another thing that they have observed in the system without the porous medium is what's called proportionate growth. So basically, if you scale up, these are 3 different time snapshots, and if you scale up the picture to fill up the whole frame, you get very similar structures. And we found that in the system with the porous medium, this proportionate growth is also observed on a statistical sense. So here we have defined this outer radius here. That's just the radius of the most advancing finger. And then we have this inner radius here that we call like the RDs, like the dense zone radius here. And the difference between these two is this RF, is the radius of, is the finger length. And basically, if we plot the ratio of RF to RD, this ratio for each experiment is approximately constant in time. So that means that if we do the same thing that was done in the model without the porous medium, if we shrink it down, we get similar figures on a statistical sense. Not like a really matching one-to-one, but they have like that quantity is preserved. And then something else that we have observed is that the region inside this compact zone is characterized by very intense ganglion activity. And you see here there are 3 points that I marked, one blue, one red, and one green, and they are these 3 points here. This is just a zoom in the segment there. And what I measure here is just like a binary variable. If you have like a liquid, then it's here. If the point there is filled with air, it flips there. So you see that there are some points, for instance, this one here, where it keeps on flipping. It doesn't change state just once. So we can count the number of times that a given pixel flips a state between a liquid field or air field. And we can call this activity order number here. So for that one here, it would be 1 because it flipped just only once. And then this point here, it flipped 3 times. So I give it flipped 5 times. So the activity order for that one is 5. And we can do this for all the pixels, and we get to this type of matrix here, which I call the flipping matrix. And it just gives an idea of how intermittent this dynamics is. It's a bit hard to visualize here because of the color map. So here we have the same information, but on a 3D plot. And you see that now we have x and y here. This is the geometrical coordinate. So this is the model. If you see from the top, you're seeing like the whole model. And then the height of this mountain is how much that point has flipped its state in time. So we have these 3 things. The information of these 2 is basically the same. It's just a color map here. And this is the invading matrix that I explained before. And we can do this for the whole phase space that we have. And we see that on this region here, that's where we have these taller mountains. So that's where you have more flipping, more intermittent dynamics. So we have characterized this dynamics with this global measure here that gives a probability that a point that has been reached by air will flip again. So this is one number that we associate with one experiment. And that's what you see in the heat map here. And then the points that are marked here, this is the actual experiments, and the rest is interpolated. The data in the background, and we see that as you move towards this region of the diagram, which is again high pressure and lower viscosities, that's where this heat map increase. So that's where we have higher probability of this flipping of states happening. So that's basically a measure of intermittency for the model. And then finally, for this system, we also have pressure measurements. And this is a bit of a complicated figure to explain, so I'm not going to go into details here, not to take too much time. But the main point is this is a spatial time map, and we have the data on these vertical lines here. That's where we have pressure data, and then we interpolate in the rest of the diagram. And if we take a derivative of this map, so we get the pressure gradient map. And the whole point here is the region between these two curves, red and blue here, is they correspond to the area between these two curves here. You see that there is color here, so that means that there is a pressure gradient in this zone here. And for the viscous fingering case, there is no color. This region is dark. So this is what's called the pressure screening, which is very characteristic of viscous fingering. That typically you don't really have a strong pressure gradient between the fingers. So that's why it gets stuck in place there. But in this type of domain where you have the compact invasion, you have a pressure gradient all over. So that explains a little bit the intermittency. Okay, so I'm going to part 2. How am I on time? Not too bad, you don't seem too angry, so I'll continue. Okay. And that's the steady state experiments. So here we are co-injecting two fluid phases, and we alternate the injection points. And around this region here, we see that there's a strong influence of the inlet. For instance, around here, you see this part is always white, whereas this part is always blue. But if you look around here, you cannot see the inlets anymore, and you see that it's fluctuating a lot. But you can define average quantities around here. For instance, you could measure the average saturation, the average pressure drop. And these quantities, they are functions of the state of the experiment. Basically like the fractional flow rates and the total flow rates. Fractional flow rates is the ratio between the flow rate of one phase to the other. And that's the type of thing that we want to study here. And we want to characterize this steady state. How it's reached, how it behaves if we perturb it, how it gets back to a steady state. So that's a work in progress. And these models here, the previous type of model that I showed, they are glass beads sandwiched between the two plates. This one here, they are 3D printed, so we can have a good control of the porosity and permeability of the model. This is about this big, more or less. And you see, depending on the total flow rates, you have different flow regimes. So here you see a regime where we have like this intense mobilization of ganglia. And the ganglia are typically larger than the pore size. And then if we increase the flow rate a lot, you get to this type of domain where it's just a bunch of tiny little droplets, lots of bubbles that are typically smaller than the pore size. And this starts to look like a single fluid with a different viscosity. So I expect that in this type of regime, we will be again on the Darcy part of the flow rate curve that Alex explained before. So that means that the pressure becomes, the pressure drop is linear with flow rate, whereas here it's not. Here I'm measuring the saturation in a little box there. And you see that initially this box is completely blue, so the saturation is 1. And then once the front reaches the box, it drops and it reaches a steady state. And one interesting thing that was somewhat surprising to me was that actually, it's almost like a steady state front that is approaching a zone that is filled with just one phase. It really does not take very long for the steady states to be reached. It's almost like a shock wave of a fluid that comes almost already at steady state. And we are investigating this by changing the conditions. So here it's, let's see, it was a water flow rate and a silicon oil flow rate. So I just increased them both a lot here. And you see a completely different regime there. That's lots of tiny, tiny drops. And again, like the steady state is reached very fast. And then it fluctuates on top of that quantity. So one thing that we're trying to do here is to measure the entropy of this type of system. So this is in line with what Alex explained in the beginning. It's a Shannon type of entropy here, so it's a sum of a P log P over the configurational space. And one question is if this entropy that depends on the flow rate, on the pore area, and on the area of the wetting phase, so that's basically saturation, if that can be split into three different separate components. And I'm not going to answer that, so we're investigating this type of thing, but I'll be focusing on this one here, which is what we call the configurational entropy. So that's it's just dependent on the wetting phase area. So what we have, this is one of the pictures of the experiment, so we just digitize it. So here, black is solid, green is oil, blue is water. And here we have time, so we have a bunch of different frames like that, one on top of the other, like this. And we can make a cube like that, where this axis here is time. So this is a space-time matrix. And we can have cuts in this matrix in this direction here. So for each fixed position x, we have one of these barcode looking type of things. And here is it's showing like what's water and what's silicon in that specific line. So in that position of that line here. So each position of the line would correspond to one of these plots there. So what we can do is to integrate in this direction here to get the total amount of water as a function of time, as a function of the frame number. So that's this plot here. I'm just summing in this direction, then flipping it here. So you see that the amount of water, it fluctuates as you expect in time, like that. So you can measure a probability distribution function of these fluctuations here. And that's what we get there. And then from this PDF here, we define an entropy, a configurational entropy of that slice as a sum of P log P, where the probabilities are measured from this histogram. Okay, so in the end, with that, we can have the entropy as a function of position inside the model. And that's what we get. So that's this curve here. And what we saw is that, so the 0 here corresponds to the inlet, and that point here is mapped here. So as you go into the model, this entropy seems to increase and then fluctuate around some well-defined steady state. And then what we want to do is to understand how this entropy is a function of the properties of the system and try to see if we can move forward with the experimental verification of the quantities that Alex has shown in the beginning. So can we take derivatives of this type of thing, for instance? So we can measure a probability map for the filling state of the pore. And this answers the question, if we look at one fixed position here, we don't know any information, but if I look at that position of the system, what's the probability that that point is filled by one phase or the other? And that's done by just projecting this type of a diagram here on the X and Y plane. And you get this type of map here with colors. The colors is the probability. So 0 means that you would never have water at that point. And then red is that the point is always filled with water. And then you see that there are some channels of very low probability of having water. So that means that most of the time it's the other phase, it's the silicon phase that's flowing through these channels. And regions where you have very high probability of having water. So for instance, around here, it's most likely a little trapped cluster because the pores are very small, so there is very high chance of having water there. And this thing here, if we zoom in, we see that it has structure. And we want to try to correlate this structure with the pore structure to see if the distance between two cylinders is small, does it mean that the probability of having water is large or not? So this type of thing is what we're going to be doing next. And we can compute this probability map also in time. So by just, if we have just like one frame, if all the information that you have is one image, then you can only say associate probability 0 and 1, 0 where there is no water, 1 where the water is. And then if you add more frames, you start to build up this probability map. And it doesn't take long for it to stabilize. So one thing that I want to try to do is to see if we can measure this thing dynamic in time. So for one time, get a probability map of having given phase there, and see how this probability changed, if it does in time or not. All right, so the conclusions. So from part one, we have observed these transitions between viscous fingering and the compact displacement. And for low viscosity and the high pressures, the structure presents a proportionate growth. We still don't have like a proper explanation as to why that happens. We just observed it. And we introduced two quantities, this invading matrix and the flipping matrix, to characterize the dynamics. And there's very intense ganglion dynamics inside this compact zone, and the pressure screening is very much reduced. So basically, there are pressure gradients there. This is different from the viscous fingering state, where we don't have that. And for the steady state, we have measured this configuration of entropy, and we are studying like how it evolves with the conditions of the experiment. And we also obtained this probability map. And I have a couple of minutes, not much more, so I just want to mention these two projects here that we have been involved with. So these experiments and simulations, they're very nice to look at, even if you don't care too much about the science, just like from the aesthetics of it is very interesting. So we made this little gallery here that you can walk around and see some pictures of the experiments on the internet. So if you are interested, you can find it on the website of the group, porelab.no. And then last year, Alex and I got involved in a bit of a crazy project with some artists and an art curator in Romania that are very interested in collaborating, like the boundary between science and art. So we had an exhibition with some artwork that was based, made, inspired by things that are done by the group. So it's called Porous Matter, and there is a website too. This one here is a very interesting work. It's basically like the capillary thumb bundle model that an artist made, her interpretation of it. So that went very well. So just to finish, this is a Fracmeet, so I thought I should have at least one fracture somewhere, because I don't really work much with fractures, but I want to put this one there. And also inspired by the previous talk. So this is a fracture network that appeared in one experiment. I have no idea what's going on here. It's just a drying pattern. But then there were like some glass spheres, and I found it really interesting because they kind of like acted as focal points for these patterns. So I don't know what's the VN combinatorics of that one, but it showed up. Okay, I'll stop here.
Thanks very much, Marcel, for this interesting talk. I think the two last talks of this afternoon had to do with art in addition to science, definitely. So we have some time for questions and comments. Do you have any question? Actually, I have one, because Alex Hansen taught us about this co-moving velocity concept, which was central to the theory. But I understood that in your experiments, you drive the two fluids from the same side in the same direction. Do you take into account that co-moving velocity?
We want to try to measure it. So the experimental measurement of that is it's not very straightforward, but we want to try to measure that. We need to make many of those experiments to calculate the steady state value of the saturation, and then vary the fraction of flow rates and the total flow rates, and then the co-moving velocity will come as a derivative of this map. But it's not something that you can just like make one experiment from this way here and get the co-moving velocity there. So there is a way to get it from the relative permeabilities, but that's not how I'm trying to do it.
So part of my question was, would you be able to drive one fluid in one direction and the other in the other? Does it make sense? And so as to have the co-moving velocity equals 0 or something like that?
Yeah, so this co-moving velocity, like the intuition around it is not that simple. Like like to go with like different directions, I don't think that necessarily means that the co-moving velocity would be 0, right? Alex is the person that's best to answer this type of things. But yeah, the name is a bit. It's a bit. We don't really have. Yeah. Yeah.
So okay, so we should not understand it as the co-moving velocity in classical or relativity theory, but something else, no? Okay. So we have some other questions, please.
So the beads that you are using, do the nature of the surface matter, like which fluid like it?
Yeah, so they are water wet, so that matters. The beads, they want to be wet by the fluid that is there, the dark stuff here. So
okay.
They're glass and
no, but my question is in the context of two fluids. So whether one fluid has more affinity to wet the surface than the other.
Yeah. So like here, like the blue one is it's more. I mean the wettability. The system is more water wet than oil wet. So the water is the blue one, but it's not as great a contrast as it is in the case of the glass beads, because the glass beads, like, it's really very water wet. If we were to measure like the contact angle of a little drop, it's very small, like a 15 degrees, 20 degrees. In this case here, it's more around the 60, 70 degrees. So it is slightly water wet.
Mm-hmm.
So my question is that your Helisha cell is like you are injecting air or the fluid from the center of the glass. Suppose you could also, we did experiments where we had two glass plates which had the more viscous fluid in the middle, just a drop of paint, and then we lifted it vertically and air invaded, forming viscous fingers. So, so the pattern is slightly different. Did you try something like this, the statistics that you showed? Do you think
we are doing that on a separate project on a rheometer. You know, like a rheometer is basically two plates, and like what was shown, like on the first talk was shearing, but we are lifting that instead,
it, yes,
and then seeing like the air that enters from the
that's
sides.
also viscous fingers, but the fingers some fingers get sort of stopped because as they move forward, they start fighting for space because the space available is. So their nature would be completely different. I mean, you could check that.
Yeah.
Number one. And number two, I was just in a question answer, I mean, to somebody who asked. I suppose this is just a question to you and Alex and everybody else here. That I think Bodhi asked himself that if we place some fluid which is having intermediate viscosity, let's say you have higher less viscous moving this side, and you want it to be on the opposite side, right? So it has to be even less than that. Yeah, no, I don't think so. I can't think of an arrangement like that. Yeah, but it's interesting, yeah, to see. Okay, thanks. Nice talk.
Thanks.
Thank you. Other questions? If not, let's thank all the speakers of this session, including Marcel. And we close the session now for dinner. Thank you for coming.